Hi, I'm Estiven Martinez, and this is my AP problem number 5. So, CO2 gas can be generated in the laboratory by reacting potassium permanganate with an acidified solution of sodium chloride. The net ionic equation for the reaction is given right here. A 25 milliliter sample of 0.25 molarity NaCl reacts completely with excess KMnO4. The CO2 gas produced is dried and stored in a sealed container at 22 degrees Celsius. The pressure of the CO2 gas in the container is 0.95 atm. For part 1 of A, we have to calculate the number of moles of Cl minus aqueous present before any reaction occurs. So we're going to use the equation molarity equals moles over liters. So we convert the 25 milliliters into liters by dividing by 1,000, so we get 0.025 liters, and the molarity is 0.25. So we set the molarity of 0.25 equal to x over 0.025 liters, and then we multiply the 0.25 molarity by 0.025 liters, and we get x equals 6.25 times 10 to the negative third power moles of Cl minus. For part 2 of A, we have to calculate the volume in liters of CO2 gas in the sealed container. So we take the moles of Cl and we divide it by 2 to turn into moles of Cl2, and we get 3.125 times 10 to the negative third power. So we set all the values of the PV equals nRT equation in. So the pressure is 0.950 atm. The moles is 3.125 times 10 to the negative third moles. The constant is 0.0821 liters times atm over moles Kelvin. And the temperature is 295 Kelvin. So after we plug it in, we're going to divide this side by 0.95, and we're going to end up getting a volume of 0.0797 liters of Cl2. For the next few problems, we have to use this data table. So, for B, we have to use information in the table to determine the order of the reaction with respect to each of the following. So, for Cl minus, I set the trial 2 over trial 1. So we plug in the concentration of trial 2, and we divide it by the concentration of trial 1 to the x power, and then we set that equal to the rate of disappearance of trial 2 over the rate of disappearance of trial 1. And after we divide this out, we get 3 to the x power is equal to 9, and 3 to the x power has to be 2. So in respect to Cl minus, the order of the reaction is 2. For part 2 of B, we have to find the order of reaction for MnO4 minus. So I set trial 2 over trial 3, and so we plug in the concentration of trial 2 over the concentration of trial 3 to the x power, and we set that equal to the rate of disappearance of trial 2 over the rate of disappearance from trial 3, and we get 2 to the x power is equal to 2. So 2 to the first power is going to be equal to 2. So in respect to MnO4 minus, the order of the reaction is 1. So for C, the reaction is known to be third order with respect to H plus. Using this information and your answers to part B above, complete both of the following. So for the first part of C, we have to write the rate laws for the reaction. So here's what the rate law would be without knowing the orders of the reactants. But after we plug in the orders of the reactants we found from part B, we get rate is equal to K times the concentration of Cl minus to the second power times the concentration of MnO4 minus to the first power times the concentration of H plus to the third power. So for part 2 of C, we have to calculate the value of the rate constant K for the reaction, including proper units. So I used the trial 1 concentrations and the rate of disappearance. So I plugged in all the concentrations to the rate equation we got in part 1 of C, and so after you multiplied it all out, we got K times 1.17 times 10 to the negative 5th power is equal to 2.25 times 10 to the negative 8th power. So we divided 1.17 times 10 to the negative 5th power to 2.25 times 10 to the negative 8th, and we got K is equal to 1.93 times 10 to the negative 3rd molarity to the fifth times seconds. So the way I got the units is I set molarity over seconds is equal to K times molarity to the sixth power. So I divided by molarity to the sixth power. So you got it on this side. So you cross out the molarities here. So you get K is equal to 1 over the molarity to the fifth power times seconds. D asks if it is likely that the reaction occurs in a single elementary step. So if the orders of the reactants were the same as the coefficients of the balanced equation, then the reaction occurs in a single step. However, the orders of the reactants aren't the same as the coefficients, so the reaction doesn't occur in a single elementary step.